So last week we came to what's really the most important concept in the whole semester, that of electric field, and we'll see that we've seen already that that's not the only kind of field, because we talked about gravitational fields as well, but we'll eventually get to be talking about magnetic fields, which are different. And the idea is that a charged object fills all of space, every single location in space, with this electric field. You can't see it with your eyes, but we know it's there because if you put a charged particle there, it'll be affected by the field and it'll start to move. And we define the direction of electric field as the direction a positive charge would start to move, would feel a force when it... And we figured out that the electric field made by a single point charge was describable mathematically by this equation, that the field depended on the amount of charge. So Q is the amount of charge in the point, it's the charge of the point charge. It's a signed number, it could be positive or negative. And the vector R here points from, this is very important, from the charge that's responsible for the field, which is called the source charge. And there could be more than one source charge. The source charges make up the surroundings of, and we don't have a system yet, so there's not necessarily anything there to be affected by the field. And the vector R points from the location of the source charge to the location in space that where we want to know the field, where we're going to eventually put a charge to measure the field, perhaps, or to be affected by the field. That's called the observation location. And we calculated E, and we thought in recitation about how you'd use more than one charge to make some kind of electric field or make it zero somewhere. The thing that relates field to force is that once you've got some source charges making up your surroundings, they're responsible for an electric field everywhere in space. And so if we choose some charge as our system, things making the field, but a different charge, and we put it at some location in space, it will experience a force that's proportional to the electric field. And it also depends on the charge of the object you're putting there, the charge of your system. So a 1 nanocoulomb charge would feel a force F, and a 2 nanocoulomb charge would feel a force 2F. And the direction is given by this product. So if the charge, your system is positive, it's going to feel a force in the direction of the field, and if it's negative, the force will be opposite to the direction of the field. And what questions do you have about this before we go further? Okay, so one question you may have is this just a calculational convenience, or is this thing real? And there's a thought experiment we can do that sheds some light on that question. So I need somebody in the back row. James, could you hold up a positive charge, please? There we go. So James is holding up a positive charge. And I'm going to measure the electric field right here at this location. And I find a field this way, pointing away from the positive charge James is holding. Now James is what, about 30 feet away, you'd say? Okay. So at some point, James is going to move this charge a meter in some direction or other. And I'm going to start a stopwatch when he does that. Okay, so go ahead, move the charge. Okay, so James moved the charge, and I start my stopwatch. And my stopwatch is in nanoseconds. So it goes 1 nanosecond, 2 nanoseconds, 3 nanoseconds. My electric field detector is still pointing away from the position the charge used to be in. 25, 26, 27, 28, 29, 30 nanoseconds. Oh, suddenly I detect a change in the electric field, and now it's pointing a different direction. Thank you. So it took 30 nanoseconds after he moved that charge for the information that that charge was in a different location, and therefore the field at this location was different, to get to me. Now what's the deal with 30 nanoseconds? Yeah, the speed of light is about a foot per nanosecond. 3 times 10 to the 8th meters per second. So about 30 centimeters per nanosecond, which means that it took the distance divided by the speed of light for information in the change of field to reach me. And during that time, I was still detecting a field. Okay, my little proton on a spring was still feeling a force, and it was pointing away from the original location of the charge that James was holding. So that field seemed to have an existence independent of what happened over there for the time it took information to get transmitted. So something was there. Something was exerting a force on that charge. And this effect is called retardation. It's a relativist. And it's related to the fact that nothing can travel faster than the speed of light, including information about electric fields. And we'll see that retardation plays an important role in our understanding of electricity and magnetism as we move along. To talk about is superposition, and that means suppose we have more than one point charge. The world is made of charged particles. There's usually 10 to the 23rd of them around at any given time, and most objects are neutral, but occasionally we get some unbalance. And so we tend to have situations where there are lots of charged particles around. And so how do we account for an electric field made by lots of charged particles in the surroundings? The superposition principle, which we talked about also, has two pieces. So at some location in space, our observation location, the net electric field at that location is the sum of the contributions of electric field of all the charged particles around. That's not a big surprise, and since field is a vector, it's a vector sum. The other thing that we actually worked with in recitation a little bit on Thursday is that no matter how many charged particles there are, the contribution of each charge is unaffected. So here's a charged particle making an electric field here. This is our observation. And it's very important when we draw a vector representing electric field that we indicate the location where we're talking about, where we're measuring the electric field. And as usual, our convention is that the tail of the vector, the non-pointy end, has to be put at the observation location to communicate the fact that that's where we're measuring the field. But if I put another charged particle in here, and it could be any sign, that does of the first particle. The fact that there's another particle in the way doesn't matter. It's still creating its own contribution to the electric field throughout all of space. Now, the net field here is going to be different because this charge is also contributing a field here. And since it's twice as close, that contribution, if they're the same charge, should be 4 times as big. But it didn't change E1. So there are two pieces to the superposition principle. One is the net field is the sum of the contributions of all the charges in the universe, really, that are making a field. And two, putting more charges around doesn't affect the contribution of any particular charge. This is great because it would be really complicated if it did, so it makes our lives simpler. So today, what we're going to talk about is a very simple combination of charges called a dipole. We actually alluded last week to something that we'll come back and really understand better in chapter 15, which is that if we have a macroscopic spherical object that's got charges spread out all over its surface uniformly, which we might do by, if we a marble and we rubbed it with silk, it might end up positively charged, or if we had a ping pong ball and we rubbed it with wool, it might end up negatively charged. The electric field somewhere out here, due to a spherically symmetric, and I'm drawing it in cross-section, of course, this is supposed to be a cross-section of a sphere, not a circle, is the same as if Superman came along and squashed our object down to a point, and all the charge was at a point at the center of the object. So E is 1 over 4 pi epsilon 0, the total charge of the object over r squared, where it's at the center. There's another very interesting feature of spheres which is entirely due to the superposition principle, and we can actually work this out with calculus, which we'll do in chapter 15, which is if you put an observation location inside the sphere, this looks to these charges, and it's a lot farther from those charges, right? But it turns out the net contribution when you add this up adds up to 0, because these charges make kind of big fields pointing away from them, and these charges are farther away, but there are a lot more of them, so they make little fields pointing away. And so if you're inside this sphere, the contribution of charges on the outside of this hollow sphere is actually adds up to 0. Yes, Henrik?
Is that every point within, inside, or just the...
Every point. That point, that point, that point, that point. Every point. Tristan?
So I think I used about the direction of the R vector, and so I don't understand why you have the tail of the arrow at the observation location there, but on the sphere you have the tip of the arrow at the observation.
Okay, so this is an important distinction. So and the distinction is the distinction between R and E. We're talking about two different vectors here. So in our example here, the vector R points from the source to the observation location, but the vector E, which is the electric field at that location due to the source charge, we draw with its tail at the observation location. So we're keeping track of two different things here. We're keeping track of R, which is the vector from the source charge to the observation location, and we're also keeping track of the effect of that charge. That's the electric field, and that's pointing in whatever direction it's pointing in. Question? Other questions? Okay. So what we're going to talk about today is a simple combination of charges. It's called a dipole. And a dipole is simply two charges with equal and opposite, two particles with equal and opposite charges, which we call plus and minus q, separated by a distance s. And this is a slightly tricky notational thing. In this equation, Q can be either positive or some charge. When we're talking about a dipole, if we wanted to use exactly the same notation, probably what we'd have to do is say the charge of that particle was the absolute value of Q, and the charge of this particle was minus the absolute value of Q, to be utterly notationally consistent. And that's just annoying, especially if we're going to end up doing a lot of algebra. So we're going to say here that Q is a positive number in this argument, so this is plus Q, and that's a minus Q. And what we're going to do is add up consider a combination of charges like this and see what we can figure out about the net electric field in the space surrounding a dipole. Why is this important? Well, if you've taken a fair amount of chemistry, you probably know that lots of molecules are dipoles intrinsically. So an HCl molecule, for example, is a dipole. Water molecule is actually a dipole, interestingly, because of these unshared electrons on the oxygen giving us some negative charge here, and each of the protons is a little bit positive. The net effect is as if we had a positive charge there and an equal negative charge there. Note that a dipole is electrically neutral. So we can't actually just use this equation to describe a dipole because the net charge of a dipole is 0. So we're actually going to have to be a little more creative in adding up the contributions of both particles. So let's that's not the one I want. This one. Okay, so here is a dipole. Our convention is always that red is positive and blue is negative. So this is a proton and electron. It could be something else. And what we're going to do is just start out by adding up the contribution of each charge to the net field at a bunch of different locations. And so we'll start, so this is the vector R, and we're drawing R from the center of the dipole. We're going to say the location of the dipole is at the center of the dipole to the observation location. But of course, when we actually add up the effects of this charge, we have to have an R positive that goes from there to there and an R negative that goes from there to there. So the distances of these charges from the observation location is slightly different. And so the green arrow represents our the vector to the observation location here. And the red arrow here is the contribution plus charge, and the blue arrow there is the contribution of the negative charge. How are we calculating them? We're actually using this equation to calculate the contribution of each charge. And when we add those up, you can see that because the positive charge is closer to this location, its contribution is larger, so the net field is the vector sum of those two vectors, and it points that direction. Now this is a slightly more less obvious, more interesting location here because it's not on the axis. It's still true that the distances to these particles are somewhat different, but the angles are different too. So the positive charge now has a contribution going like this, can you see in your minds what the contribution of the negative charge, the direction of the contribution of the negative charge? It should point toward the negative charge, shouldn't it? So that's going to look like that. A little shorter because it's a little farther away. And we add those two vectors to get the net field. We get in that direction. And now the field is not in the direction of R at all. It's neither parallel nor anti-parallel to it. It's in some other direction completely. Now we expect this to be symmetrical, so at a location that's just on the other side of the axis, we should expect the same thing. Try to imagine the field of the negative charge here. Okay, it looks like that. We add these and we get a net electric field pointing in that direction. Okay, here's an interesting location. So again, try to visualize positive charge, the electric field of the negative charge, the net field. Down here, it's just going to be the mirror image. Now we're at an interesting location because we're equidistant from the two charges, right? So can you see what's going to happen here before we actually do it? So imagine the contribution of the positive charge. Goes like that. The contribution of the negative charge like that. Looks like the y components are actually equal and opposite. So it looks like we're actually going to get an electric field in that direction, which is an interesting one. It's actually perpendicular to R here. And presumably the same thing is going to happen on the other side of the axis here. So this does not look like the electric field of a point charge, which just points either away from. Okay, we've got positive charge, negative charge. Now the negative charge is a little bit closer. We get a field like this. Down here, positive, negative, kind of like that. Over here, here's the positive charges field, there's the negative charges field. Positive, negative, and finally here, positive, negative. So that's kind of an interesting pattern of field. And note that, of course, in each case, the tail of this arrow representing the field is at the location where we're measuring the field. So the tail of the arrow is at the observation line. And so this is a slice. Obviously, this is a 3D thing here. And so presumably we could calculate the field in some other plane, say the xz plane. And in fact, it pretty much ought to look like this. If we just kind of rotated this picture, that's what it would look like, right? So we get a 3D pattern of field in space. But this is a very characteristic pattern of field. This is the electric field due to a dipole. And it's a field that, so this pattern is important. It's not all algebra in this class, but recognizing patterns of field are actually important. Now there's something to note here. This is called the dipole axis. A line going through both charges is the dipole axis. And on the axis of the dipole, the two locations where we calculated the field, it's pointing in the direction sort of from the negative charge to the charge, right? And this other axis, the other sort of symmetrical axis of symmetry, is perpendicular to that axis. We call that the perpendicular axis. And on that axis, the field is pointing in the other direction, and it seems to be about half as big as that field. So we'll see if that holds up when we actually start trying to calculate things. So questions about how we did that? Yes?
When will we need to know the shape of a dipole electric field?
Fairly often, because dipoles occur so much in the next chapter that we can actually we can make them fairly easily. And but so one thing to keep in mind though is you can always figure out, if you know which is a positive charge, which is a negative charge, you can always graphically figure out the direction of. Okay. Now this demands some care. It's nice to ask a computer to do it for you. On the perpendicular axis or the dipole axis, it's actually easy to get the direction right. But this is a pattern that's actually important. Now we could calculate it on a, so you can see here that one of the things we've done, and this will be something you'll end up doing eventually in your own computer calculations, is we've put the observation locations on a sphere, on a circle really surrounding this dipole. And that's kind of a common thing that we'll be doing, is using a circle or sometimes a cylinder depending on the symmetry of our distribution to observe. So that gives us a graphical representation, but it doesn't give us any algebraic expressions that we can work with. So let's see though, before we try to make an algebraic expression, if what we can do about trying to get a sense for effect. So here's what we're going to do. Here's a dipole. What we're going to do is we're going to do exactly the same procedure, add up the field of the positive charge, field of the negative charge to get the net field, but only along this perpendicular axis. But we're going to do it at a whole bunch of places along the perpendicular axis and see if we can guess how it's falling off with distance, how it should be falling off with distance. If it was a point charge, it'd be 1 over r squared, so the very least we can see if it looks like 1 over r squared, okay? So here's our first location. That's the field of the positive charge, that's the field of the negative charge. I'm using kind of a big scale here because as you see, it falls off kind of fast. Okay, so that we're calling a distance d. And down here, what we're printing out is the distance and the magnitude of the field divided by the magnitude of this field. So when the distance is 1 times d, the ratio of the magnitude of the field to the magnitude of the field at a distance of 1 times d is just 1. Right? So we're okay. But we'll be able to see something else interesting. So now we're going to step up in steps of about d over 3. So we've got, okay, so now the field is smaller. Here the distance was one and a third times d, and the magnitude of the field is 0.44 as big. Here we've got 2/3. Here now we are at 2 times d. Okay, and we can, so if this was a 1 over r squared dependence, we'd expect the field to have dropped by a factor of 4, right? So let's see what it's dropped by. where distance is 2d, and the magnitude is not 0.25. The ratio of the magnitudes is not 0.25. It's actually less than 0.25. So it's not a fourth. In fact, if you work that out, it looks like a roughly almost a ninth as big. So let's go out to 3D and see what we get. Notice that the magnitude of the field ends up being very small because even though the magnitude distributions, they have a big components in the plus and minus y direction, and those things are equal and opposite, so they add up to 0. Okay, so now we've gone up to plus 3D, and if it was a 1 over r squared field, we'd expect that by now to have gone down by a ninth. And instead, it's a lot smaller than a ninth. It looks like about a 27th. Guess might be that this is a 1 over r cubed distance dependence, just from what we're seeing here. So let's see if we can work that out algebraically. So our next task is to actually try to do algebra to derive an expression for the electric field of a dipole along the perpendicular axis and the dipole axis, frankly, and see if it turns out to be a 1 over r cubed dependence. Now at this point, we're going to do a lot of algebra. And we're not going to spend most of these lectures doing a lot of algebra, but I think it's important to see what the process is, what we're actually doing to get this. So we're going to bite the bullet and do a lot of algebra right now. And so let me orient the dipole the way I've got it oriented in my notes, so that when I make a mistake in algebra, your job is to catch and correct mistakes in algebra. We can survive it. So here's our dipole. Here's the dipole axis. We're taking a location on the perpendicular axis. We're going to call our observation 0, y, 0. That's going to be the location of our observation location. We're going to put our origin right in the center of the dipole. And since the distance between the particles is, that means that the location of the positive charge is a plus s over 2, 0, 0, and the location of the negative charge is a negative s over 2, 0, 0. And each of them has, so this is a charge minus q, where q is a positive number. This is a charge plus q. And now we just are going to use the superposition principle. So we're going to figure out the field of the negative charge and the field of the positive charge algebraically and add them algebraically and see what we get. And since this is a y, it could be a y on this axis, right? So to start out, we want the field of the negative charge. And so our vector r, we'll call it r minus, because it's going from the negative charge to the observation location, okay? Starts at the negative charge. R, I'll call it r sub m for r minus. So R minus is just the observation location 0, y, 0 minus the source location, which is negative s over 2, 0, 0. And so we get an s over 2, y, 0. I don't think we've made any mistakes so far. And that makes sense because the x component's positive and the y component's positive, right? So now we need the magnitude. That's going to be s over 2 squared plus y squared, the square root of that whole thing. And so r hat is equal to r over the magnitude is going to be an s over 2, 0, 0 divided by s over 2 squared plus y squared square root. I don't think I did anything wrong so far.
Good.
Yes. Yeah, Jonathan?
Isn't it s over 2 y 0?
That is what it says.
R hat. Yeah. S over 2 y 0.
You're right. I did make a mistake. Thank you. Okay. Okay, so now we can write out the electric field by using the electric field of a point charge equation. And so E minus, I'm going to give myself a little more room here, E minus is 1 over 4 pi epsilon 0. The charge is a negative q. R squared is the magnitude of R squared. So that gives us an s over 2 squared plus y squared. Take the square root and square it. We multiply it by r hat and we get an s over 2 y 0 over s over 2 squared plus y squared to the 1/2. And we can write that a little more cleanly by multiplying these two things together and getting this to the 3/2. So it's equal to 1 over 4 pi epsilon 0 negative q over the quantity s over 2 squared plus y squared to the 3/2 times s over 2 y 0. All right? I have to do it again for the positive charge. So R plus, we'll call it R sub P, is the observation location 0, y, 0 minus the location of the positive charge, which seems to be plus s over 2, 0, 0, and that gives us a negative s over 2 y 0. The magnitude of R plus is going to be minus s over 2 squared plus y squared, square root of that. Same magnitude as the other one because they're the same distance from the charge, right? Rp hat is therefore minus s over 2y0 divided by s over 2 squared plus y squared square root. And the electric field is therefore E plus, so 1 over 4 pi epsilon 0. We have a plus Q over the magnitude of R squared. So again, we have s over 2 squared plus y squared times a minus s over 2y0 s over 2 squared plus y squared square root. And simplifying slightly, we get a 1 over 4 pi epsilon 0 q over s over 2 squared plus y squared to the 3/2 times a minus s over 2y0. Now, how do we get the net field at that location contributed by both charges? We just add them up. So E net it may actually be simpler to look at components separately, actually. So let's think about the y component. 1 over 4 pi epsilon 0 q. So this is e plus e. Let's do e minus y plus e plus y. So that's a 1 over 4 pi epsilon 0. We have a minus q over this whole thing to the 3/2 and times y. This is the component of the vector component. And then plus a 1 over 4 pi epsilon 0 plus q over this whole thing to the 3/2 times a y. And we see that these are the same except for the sign, so it's going to add up to 0. So the y component is just going to add up to 0, right? And that's what we saw when we did it graphically. Questions?
I'm very confused where the negative went from the magnitude of RP to the R hat. It went from negative
Oh,
S.
well, negative s over 2 squared is exactly the same thing as s over 2 squared.
Okay.
So I dropped it because then we get the same denominator.
Okay.
Yes?
I think what's P in the M subscript?
So that P stands for the positive charge, M stands for the negative charge. And so E sub M was the field due to the negative charge at this location. And E sub p was the field due to the positive charge at this location. So we had to calculate those fields because we didn't know what they were, and then we have to add them up. And
Why n and not n for negative?
oh, I was calling it minus. N might have been better. Okay. Other questions? Okay, so let's see what we get for the x component. And now you have to help. So E minus x plus E plus x. So we have a 1 over 4 pi epsilon 0. Given we have that denominator, which is the same. In the top, we have a negative q times s over 2. And for the positive charge, we have a 1 over 4 pi epsilon 0. Same denominator. And here we have a q times a negative s over 2. So it looks like the x component is going to end up being 1 over 4 pi epsilon 0. There's a well, so we have a negative q times s over 2 plus a q times a negative s over 2. So that gives us a negative qs. Over s over 2 squared plus y squared to the 3 halves, which says that the electric field is pointing in the negative x direction, which looks right. And so if we put this all together, the magnitude of the electric field at on the perpendicular axis is just going to be equal to 1 over 4 pi epsilon 0 qs over s over 2 squared plus y squared to the 3 halves. Now, in a really important sense, it doesn't make sense to call that variable y. Why not? Like that. So if it's a molecule, it can rotate, okay. So a dipole could have any orientation in space, and what we really want is just, it's on the perpendicular axis. So in many cases, we just end up calling the distance from the center of the dipole r to take into account that so we can replace this y with an r. If you like, we're switching to spherical coordinates. So we got, after a huge amount of algebra, an expression for the magnitude of the electric field at some location on the perpendicular axis of a dipole. Now notice that there's not an r hat. I mean, we can't just multiply by an r hat and get a vector, because this isn't even remotely in the direction of r hat, right? So here's our dipole, minus plus. We're at some location here. You know, that would be r hat, but the field is that way. So in this case, and in a lot of other cases, what we're going to end up doing is working with a magnitude that we can calculate and then getting the direction by looking at the situation and seeing what direction it has to point. So you would, if asked to get the field of a dipole at some distance d from this dipole, you could calculate its magnitude using this, and then you could say, well, I know this is the, so its contribution is going to be here, and here's the positive charge, so I think the field is really going to be pointing in that direction. Yes?
It's that equation that we just found for the perpendicular magnitude.
It's on the perpendicular axis, and we'll talk about the dipole axis in a second. Serena?
So if we would ever have a question on this, we wouldn't be asked to represent it in vector form?
No, there is, I mean, in some upper level E&M course you may derive a general expression, but it's actually in vector form. It's very hairy and involves a dot product with the dipole moment represented as a vector, and I mean, okay, so we're not going to do that. However, we still didn't answer our question, which is, does this look like 1 over distance cubed or not? Because we have an expression that doesn't, it's messy, right? So let's see if we can simplify this a little bit. I'm going to erase this. It's actually in the book, so it's all right. So we have on the perpendicular axis is equal to 1 over 4 pi epsilon 0 qs over the square root of s over 2 squared plus r squared to the 3 halves. But let's suppose, now this is something we're going to be doing a lot of in this course, thinking about what does the field look like when you're not actually standing right next to this source, but you're a little distance away. So let's say, what if the r, which is now our distance from the center of the dipole to your observation location, what if r is actually bigger, a lot bigger than the dipole separation? Okay, so dipoles are kind of, and you mostly are measuring the field at a distance that's farther away than the dipole separation. What approximation can we make to simplify this equation now? So if r is a lot bigger than s, then r squared is likely to be even more, a lot bigger than s over 2 squared. So, yeah, so we could say, let's neglect s over 2. Let's say s over 2 squared is very small compared to r squared. So this is approximately 1 over 4 pi epsilon 0 qs over r squared, which in fact gives us a 1 over 4 pi epsilon 0 qs over r cubed, which is what we guessed from looking at just our calculations. We guessed that it was going to fall off like 1 over r cubed, and it actually does. Yes, Charles? What counts as significantly larger? That's always a question that everyone asks. So if r is, and I think it depends on exactly how precise you need to be, but suppose that the distance was 10 times the dipole separation. That's certainly significantly larger, right? 5 times, maybe. 0.3, definitely not. But let's actually look at a program that that calculates this here. So here is a program that calculates 2 things. It calculates the approximate field of a dipole, the magnitude, so that's 1 over 4 pi epsilon 0 times 2qs over r cubed. And then it uses this exact equation here, s over 2 squared r cubed. And it just plots both of them as a function of r. So, okay, we're starting at, so the x-axis is the ratio of r to s. Okay, so it's a ratio of the distance from the dipole to the dipole separation. And so we see that when the exact calculation is the red and the approximate calculation is blue. And we see that when you're only a distance s away from the dipole, you're off by 40%, okay? Because it comes out to 1 instead of 0.6. But by the time you get to 2 times s, so you're twice as far away as the dipole separation, it's pretty good. It's actually better than you think it ought to be. And after that, it's pretty much indistinguishable. So it's a much better problem, I think. Which means that we are almost never going to bother using this equation. So approximations are your friend, and this is quite a good one. So, questions about what we just did. So all we did was apply the superposition principle. We did it with algebra, though, instead of with numbers. And we got a general expression for the electric field of a dipole at some location on the perpendicular axis. Notice that we couldn't add magnitudes. We actually had to do vector calculations to get that expression. So we did have to take into account the vector nature of this, but then we... Okay, so let's see if we can answer a question. Which one is this? 13.6a. There. Okay. So, we could use this equation to calculate of this dipole location C if we knew the distance and the charge, and we knew QS and R. But what about the direction? How would we get the direction? So what is the direction at this observation location we've chosen? Okay, what's the direction? So I'm seeing 8. I think I agree. So so let's let's see how we got that. If we have negative and a positive, here's location C. The contribution of this charge would be that direction. The contribution of that charge would be that direction. So we're going to get a sum in that direction. Yes, Charles?
Do dipoles always have like a field that goes from positive to negative like that?
Dipole, yes. So are you asking, is the pattern that on the perpendicular axis the field will point away from the positive charge and toward the negative charge? Yeah, you can set a bunch of examples, but yes, that's correct. Okay, what about what about that one? So what do you think? 6. Yep, I agree. Okay. Questions? Okay. Now, note that we only did this for the perpendicular axis. And not surprisingly, it turns out that if we wanted to, we could do this with very similar algebra any place on the dipole axis. Now notice that on the dipole axis the field is going to be along the axis one way or the other, right? Not perpendicular. We would go through exactly the same process, which I'm not very enthusiastic about going through on the board. The derivation is in the book if you want to try doing it yourself and then checking it. It's a good idea, actually. And if we go through that, what we get to is the following thing. So that's equal to if we go through the whole thing again on the dipole axis, we get that the magnitude of the dipole is equal to 1 over 4 pi epsilon 0. We get a two QSR over an R minus S over 2 squared times an R plus S over 2 squared. And then if we make that situation, so our observation location is farther away than the dipole separation, and again we see that it is far away before it starts being a pretty good approximation. We're going to end up with a 1 over 4 pi epsilon 0. If we're going to be able to neglect these S over 2's, we're going to have an R to the 4th. We have a 2QSR over R to the 4th, so we end up with a 2QS over R cubed along the axis. So notice that the field, the magnitude of the field on the dipole axis at any distance is actually is the magnitude of the field on the perpendicular axis. And we saw that in our glow script program here. So we're saying that the magnitude of this field at a distance r is half the magnitude of that field at a distance r, and that's in fact what we saw when we calculated it exactly. And in this equation, so Q is the absolute value on charge. S is the separation. And R is the distance to the observation location. And so we have these two equations that we're going to using a fair amount. So notice that these equations suggest two different ways to increase the field of a dipole. So suppose we have a dipole of separation S, charge minus Q and plus Q. We measure the electric field here. It has some value E. If we doubled the value of each charge, so we just double Q, we double the magnitude of the electric field, right? So if we had minus 2Q plus 2Q over S, we'd actually get twice the field. But there's a different thing we can do looking at this equation to make the field bigger. Instead of doubling the charge, we can actually just increase the separation between the two charges. So have a minus Q and a plus Q, but they're separated by twice the distance. We're still going to get a field twice as big as the first. Why is that? That's just like saying just magic.
Yeah, just at the top right there.
You see it in the equation, but think about the fact what we were doing is we were adding the fields. When we did this calculation, what we were doing was we were adding the contribution of the positive charge and the contribution of the negative charge. So if these two charges were exactly in the same place, they were on top of each other, would those contributions be different? No, because the distance would be the same, right? They're not quite the same just because at any observation location, one of them is closer than the other. And the one that's closer than the other contributes a bigger amount to the field. So as you pull them farther and farther apart, at any observation, one is now a lot closer than the other. Its contribution is a lot bigger. So the farther apart there, and on the perpendicular axis, even though they're the same distance away, as they get, the y component gets smaller and the x component gets bigger. And so they... Now, so this leads us to define a quantity called dipole moment. And I'd like to leave those equations up. So the dipole moment of a dipole is equal to the product of Q and S, because by increasing either one of these things, you can make the field of the dipole bigger. So it's kind of a measure of the length of a dipole, how big a field it's going to produce. Unfortunately, there's a symbol for it, which is traditionally P, which is very awkward, but there it is. And in fact, even more, yes, so, and actually, we're not going to care about this and what we're doing, but you can actually, P can be a vector. So P would point from the negative to the points in the direction the field on the x-axis would point. And so now we unfortunately have a vector P that's not momentum at all, it's dipole moment, but we can probably cope with this. So dipole moment tells you the dipole strength of a dipole.
It points towards the positive, the dipole moment, the vector.
It points toward the, if your dipole was minus, then it would point that way, yeah. So it's sort of interesting to think what would happen about forces in the dipole. And so one question we might want to answer is, what would the force between, what would the force exerted on a dipole by a point charge be? So suppose we've got our dipole here. And over here we've got a point charge, we'll give it a capital Q. What's the direction? So how do we calculate the force on the dipole due to the point charge?
Calculate the force for the positive and then the negative, and then add.
We could do that. It's actually not going to work very well if the dipole is quite small and we're fairly far away, because when we try to do that, we really need the approximation. It turns out that when you're fairly far away, the dipole separation is so small compared to your observation distance that you're actually going to get a 0 if you try to calculate the forces separately. So we need that approximation. Dipole is a system, yeah. So let's see if let's ask a simpler question. How do we calculate the force on the point charge due to the dipole? First of all, what direction is it going to be? Okay, so F. How would we calculate it?
Just the charge times the dipole moment.
Times the electric field of the dipole. The charge times, yes, so F equals QE. So this would be Q times, so the magnitude of the force is Q times 1 over 4 pi 0 to QS over R cubed, where that's our distance R. Okay, so we've got the magnitude of the force by the by the dipole on the point charge. So what's the force on the...
Would be opposite.
Yep, reciprocity. So equal in magnitude, opposite in direction. So F on dipole. So they exert equal and opposite. So the dipole field is a helpful construct. One thing. So I need a volunteer. Darius, you're a volunteer. You just got volunteered. Could you hold up a dipole, please? And okay, which I want one charge in one hand. I want a positive charge in this hand and a negative charge in that hand. Okay, so here's your dipole. Now your dipole happens to be composed of a positron and an electron. So an electron has a charge minus E, a positron has a charge plus E, but it's an antiparticle. So here's my field detector. Which one's which? Which one's negative? Negative on that side, positive on this side. Okay. So when I'm standing here, I see a field. So you said positive, negative? Okay, so I see a field this way, right? Now I want you to let them go. They attract each other. They move toward each other. They annihilate each other. There's a reaction, and now we don't have a positron and an electron anymore. We just have two photons going off. But here I am measuring an electric field due to these non-existent charges for 1 nanosecond, 2 nanoseconds, 3 nanoseconds. What do you think, about 25 feet? For 25 nanoseconds, oh, oops, no electric field anymore. So for 25 nanoseconds, after the particles cease to exist, measuring the electric field made by that dipole when it was there. Furthermore, this field must actually have energy in it, because if I let my proton go, it would have started to pick up speed, right, and gain kinetic energy. So even though the original source charges no longer existed, that field was still there 5 nanoseconds after they vanished. So electric field has this reality of its own, and retardation plays an important role in what's going on in our lives. Okay, we'll practice with dipoles this afternoon.